Hi, and welcome to our second part of our two-part lecture series on comparing IPv4 to IPv6. My name is Ron Richter, and I'm an instructor here at Blue Ridge Community and Technical College. So let's get started talking about the differences between IPv4 and IPv6. So in our last lecture, we talked about the different types of IPv6 addresses. Now let's talk about the different varieties of IPv6 addresses. Unlike IPv4, where we have one IPv4 address per interface, in IPv6 world, you can have up to 3 and even 4 IPv6 addresses per interface. Different types of IPv6 addresses can vary. Each interface could have a global unicast address. Each interface may have a link local address. Each interface could be configured with a loopback address, or an unspecified address, or a unique local address, or an embedded IPv4 address. Let's start with the top first, global unicast address. A global unicast address is similar to a public IPv4 address in the respect that it's globally unique. It's never repeated again. Like a public IPv4 address, it's perfectly routable across the internet. Like an IPv4 address, it can be configured statically by us or dynamically via DHCP or other technical configuration. The link local IPv6 address is somewhat different from anything we've talked about in IPv4. Because it's used to communicate with other devices on the same local link only. Okay? These link local addresses are not routable. Okay? They're confined to that single link and cannot be routed beyond that link. Loopback address is the same idea as a loopback address in IPv4. Simply used by a host to send a packet to itself. Okay? Can be used to ping an IPv6 loopback address in order to test the configuration of the THCP stack on the local host. The configuration of a loopback in IPv6 means that the entire address is all zeros except for the last bit. So it'll be represented as : 1 according to those rules of compression that we talked about last video, or just : 1. An unspecified address is simply an address with all zeros in all the bit places. It can be represented as : /128 or just : These addresses cannot be assigned to an interface. It's only used as a source address for a packet. An unspecified address is used as only a source address when that device yet doesn't have a permanent IPv6 address, or when the source of the packet is merely irrelevant to the destination itself. And then a unique local address is theoretically similar to a private address for IPv4. It's used primarily for local addressing within a site or between a limited number of sites. They're distinguishable by the same beginning of FC00 to FDFF with a prefix of /7. The composition of every IPv6 address remains the same. We would normally divide our IPv6 address prefix from interface ID at the 64th bit, denoting the /64 prefix. When it comes specifically to link local unicast addresses, every IPv6 interface has to have a link local unicast address. And again, this merely enables the device to communicate with any other IPv6 device on the same link. Okay? And again, in this case, our link local unicast address will be comprised of 64 bits comprising the prefix and 64 bits comprising the interface ID. All link local unicast addresses will all be denoted or start with FE80 as the first 4 digits in the hexadecimal address. So as we break down the structure of IPv6 global unicast addresses, you'll see that the The prefix is actually made up of two subparts, the global routing prefix and the subnet ID. The global routing prefix comprises the first 48 bits, and the subnet ID comprising the second 16 bits to create a total of 64 bits. Now, unlike IPv4, we use subnet IDs merely for addressing purposes and not to save or retain IPv6 addresses. The global routing prefix is the network portion of the address, usually assigned by the provider like an ISP, assigned to usually a customer or a site, again, representing the first 48 bits. Currently today, all global unicast addresses start the same with bits of 001, which equate to 2000 in hexadecimal representation. So in this sample of a IPv6 global unicast address, we see 2001 :0db8 :acad :/48. This has a prefix that indicates the first 48 bits, or exactly this much, is the prefix or network portion of that address. If we want to expand this example out a little bit further, we expand the compression where the zeros once existed and replace the zeros. Now you can see the full 128-bit address, filling in the zeros that were compressed out and the sequential zeros that were compressed out. And again, we can see the global routing prefix is the first 48 bits. The subnet ID is made up of 001. Then the interface ID is simply 000, 000, 000, 000, 0010, or all zeros 200 in hexadecimal. From the perspective of how we configure our addresses dynamically in the world of IPv6, we can configure them dynamically just as if we configure them in IPv4, or we can configure them statically, just like in IPv4. The primary difference being when we configure our IPv6 addresses dynamically, we have options on how we can do that. When you configure your router with IPv6 routing, it will immediately begin to issue RA messages, or router advertisements. These RA messages can relay addressing information in three different forms. Either using the SLAC-only option, in which the prefix and the user ID are both generated using stateless address automatic configuration, which means that the assigned prefix and the second half are made by automatically using the EUI64 method or randomly generated method. The second option is using stateless automatic address configuration with a combination of DHCP. In this method, the information in the RA message, being the prefix and the randomly generated or the EUI64 method, is used to configure the address portion. Other information, namely DNS address, domain name, things of that nature, are all derived from the information from the DHCP6 server. The third option, being DHCP-v6, means that the host device requesting the IPv6 information won't get anything from the router advertisement message. The host will get all of its addressing information from the DHCP-v6 server. Interestingly enough, all of these router advertisement messages use the link local addressing that we talked about earlier. So what is this EUI64 method that we keep talking about that generates these IPv6 addresses? Quite simply, we can have the hosts generate their own IPv6 addresses automatically with no help from an outside source like a DHCP6 server. That's done by taking the 48-bit MAC address and combining it with FFFE, transforming the FFE into binary notation, inserting it into the binary representation of the MAC address, and merely flipping the 7th bit. Now, I've never gotten a good explanation why that 7th bit flip was necessary, but it just is. So in other words, we will complete the second half of our address by using the MAC address and inserting FFFE into the center of it. Convert everything into a binary, then convert everything into hexadecimal. That's one method. The second method is to just randomly generate all these fields. Which method is preferred? Well, it depends on the system. A device can use a randomly generated interface ID instead of using the MAC address and the corresponding EUI64 process. Early Windows systems would always use the EUI64 method of using that MAC address, splitting it and inserting FFFE into the center. Interestingly enough, Linux these days uses EUI64, but compared to Windows, Windows and from generation XP use EUI or use randomly generated information. Which is the best method? Well, if you think about it, in a corporate environment or a scaled up environment, it can be a bit of a nightmare as systems go down and come back up and they randomly generate their IP address. Each time they come up can be a bit of a management nightmare. The best method is to use the EUI64 method, which most modern versions of Ubuntu and Red Hat currently use.